let's have the first three support joints to handle the position, the other three to handle the orientation. In some of your exam questions, what they will give you is basically just the support configuration. You're supposed to identify is it Cartesian, spherical, cylindrical. And then at the wrist, is it a official or sometimes they will tell, sometimes they will give you the image. Again, for the first three joints of position, look at the joints. From the joint that you have to identify whether it's Cartesian, how do you know if it's Cartesian, how will the joint be? If you look at the robot configuration, it's either two types, either twisting or revolute, right? So what will you get for a Cartesian robot? What kind of joint do you have? All prismatic, so we have all prismatic. So what you see, if you are all prismatic, if you really, let's say my God, for example, what the least you can do is just look at, you just move the joint and you visualize that you're moving the joint. Prismatic will be up and down, then you look at the end of the where can you reach? What space it creates, right? So Cartesian will give you like a rectangular box type. You look at cylindrical, you will have one revolute joint, two prismatic joints. Then you roughly know all this is cylindrical. And then spherical is two orientation. Right? Okay, so this is what I identify. For the wrist, again, either it's Robic or Euler. Just look at the angle, the symbol of the angle. From there you identify whether it's Euler or Robic. Right? Again, the other for your exam, I will set up another lecture just to go through some exam questions. I give you the how do you strategize and answer this kind of questions. But right now, for continuity of what I taught you, I'm going to go through the textbook examples first. Because they will somewhat similar. How I solve these will be somewhat similar to how I solve the exam questions. Right? Okay. So exam questions, again, this is the part where either will give you individual values of this, you won't arrange it in this format. He will give you, okay, the vector n is something, you are supposed to put it in this format. So you need to make sure that you know n comes from then O, then A, and then after that whatever your position of your n is. It should be this one. Now this question, so it will be something like this. So exam question will make it one step higher. They are expected to find out this given transformation. Right? Once you are given this, so this is something you are given. Okay? P is the given. So be this format, okay? So this is my 3, 5, small, 0, 0, 1, 4, 3, 3, 5. Okay? Okay? Looking at the robot configuration that they give you. Right now, this one is clear. They tell you that it's Cartesian Robic shore. Okay? What does this mean is this? That means the P given will be a product of P Cartesian times P Robic. Okay? Make sure that you use the unrelated format. It's always remember position, why we do unrotation or compensation, because we are only using position. Due to the undesirable effects of having some motion, especially when you angle, it creates some orientation implicitly during the motion. So you have to unrotate. Right? And why are you cross multiplying? Because what you will do is this: the robot motion value. I will go to the position first. So Cartesian transformation of number. After that, once I reach the position, I will do some orientation. But this orientation is respect to the moving field. That's why we have sure that you put in the right values. So when you have P Cartesian, you know that this is an identity matrix. You have Px, Py, Pz, 0, 0, 0, 1. Okay. And your row P sure is a very long this matrix. Indicated R row P sure. Okay. Now this one is doing pure orientation. Right? It's just orientating your final transformation matrix. So because of that, your origin is not going to change. Because your origin is not going to change, 0, 0, 0, and 8, 0, 0, 0.
The unrotated PXPYPZ 是 unknown 的，应该是 unknown 的那个。可以这样子。所以我要把这边的 matrix first 过去。
It will become R, rho, your EX, EY, EZ, 0, 0, 0. Okay? From here to here, you will be doing this exercise. Okay. But what the question gave you is, I have given you this particular matrix, right? 0.354 This is what you were given. Based on your robot configuration, you know that this is Cartesian and Robichaux. This is the metric that you will find. And that's what we are doing previously. We will do comparison. You will compare the elemental values with the symbolic values on your right hand side. Okay? So because this is Cartesian, your Px, Py, Pz is straightforward. You can get this value. The tricky part is that we also go through this part. This part and compare it with this part. This matrix that you have, the Robichaux, is basically the one you see on your screen. This is very complicated.
变了。我差点要死一下。我要往那边。哦，有。
But remember, I told you there are solutions that you just have to remember. Just make sure that you need to remember this. We are just going to solve this. End of the day, your first kinematics is all about finding your joint. Be it your static values for your joint or orientation angle for your joints. Okay.
这个回家慢慢玩的，并不是自己是。如果那种直接机车就好了，他就收这个。对啊。
This was solving it, you have n minus 1, ny over nx. Okay, if you go back to the format, Do you know what's your NX and NY?
Yes.
Do you know?
Yes.
Yes or no?
Yes.
Yes, huh? Right? Based on this, you know your NX, your NY. Right? All you need to do is substitute it inside here. Okay? So the tangent equals 0.505 over 0.354.
Good.
Okay? If you look at this tangent, so-called tangent side here, this entire thing is actually positive, right? Okay, now we go back to our if it's a tangent, if it's a positive tangent, which quadrant will you like? 1, 2, 3, or 4? Sorry? 2 and 4. Okay, good. Right? So this is your principal angle that you will find. There's one angle, the other angle will be from here to here. This will be 180. Okay? So by right, I will have two values. One is 55. Right? And 180 is right? Because if it's a positive tangent, it should lie in both quadrants, right? 2 and 4. This is the part I want you all to take for. Okay, so let's say now if my tangent of my side A is negative, which quadrant will it lie? 1 and 1 and 3, yeah. Okay? So this is something I want you to take for. So if it's a positive tangent, you should know where the angles are. So you will generally have two answers, two sets of angles for you to figure out. Okay? So once you find your side A, you have to find your side O, which is tangent inverse minus nz over nx of ny. Okay? Again, you know your nx, ny, and nz. You also know your side A's, okay, from the previous workings. You just have to substitute them in, you will find two values. More value for this. Then your third angle is side N, which is AY. Okay. Again, you know your these values, you know AY, OY, AX, A inside A also. So you know these values and just plug in. Again, you This will be the general steps for you to solve your validation portion. If it's Euler, safety negative, you use the Euler formula result. Start from this step first. Always start from
O的话，我的 tangent 是要 negative 啦，所以我就会 force 在我的 y 跟 equal 3了。如果我要找 phi O 的话，那 phi O 是 negative 嘛，所以我就 force 在3跟1了。negative，那 negative，这个 phi O 这个是 negative 1，所以有时候不一定 negative。不是在不是在第3跟第1，没有，这个全部，然后这是sin 5或 cos 5，不是没有，这不是。然后就懂它其实是你看你answer，看我answer，这个，你看它写 all positive 吗？因为这两个都是 positive 嘛。或者是 tangent positive 啊，所以你这个。它这个是从这边来才找到一个answer吗？不是吗？没有，你看这个，你说的 tangent 是 positive，对吧？对 ，tangent 是这个。你就这样讲，你可以看整个 positive 这两个你这样想，你看是不是 positive？ should be a negative 吗？你 n7 有 negative， n6 是 negative 是什么？n1 positive 哦，对啊 ，ny 是 negative，ny sorry。
Generally, if you look at your section D of exam, the first portion is your professor efforts part, right? The second part will be the one I'm teaching in right? So, from lecture 1 to 5, it may add 2 questions per lecture, definitely 3 questions, choose 2, right? So there will be only 1 question from the part. 2 questions will come out from lectures 1 to 5. My advice is that it's one of the very simple, it's easiest in terms of memorizing, but it's a rather straightforward way of solving it. It's not very complicated. Just follow the steps, more or less.
3个 question，
Sometimes you may really
3选2，2个它的是这个跟之前的那个Mr. Tan 那个叫马的那个。看哪一个那个名字我一个。
Any questions so far? Okay, I presume no means here. All will take up these questions. Okay, again I tell you this is the more simple one, it's easiest. Just follow it. Okay, let's move on to lecture 5. And then we will do some examples there. Again, you have example 0.12 and 2.2. Practice that on your own. I've given you a step to do it on time. Yeah, some of you or if you need the answer, just you can refer to the next to get the answer or just email me or just email the answer. Right?
可以乱来的，不一份，一份。
你要吗？你是老板哎。
对不起，谢谢。
要求到，但是不敢。
我一手机就够。
要不要？我借你，我借你。
Okay, the next portion that we are going to do is actually the frame assignments. Now you, in your everyday, let's say if you work on engineering firm, you are doing robots, you will experience configuration of robots. Right? Is there a systematic way of assigning frames other than one person does it this way, one person does it another way? Right? So many years ago, academicians have come up with this DH transformation parameter. Right? DH supposed to mean derivative right? So they came up with a systematic way. I give you any robot configuration with joints, with links, and just need to assign them in a very systematic way. And once I assign them, I also have a set of solutions that I can use. Right? So this lecture will cover how I go about assigning the frame to the robot. And then once you assign these frames, you are able to get the transformation matrix easily. Right? At the end of the day, you just want to get the symbolic form versus what you have given to be some numeric form. Think about that. Okay? Inverse and forward. But before that, I want to talk a bit about degrees of freedom. What is actually degrees of freedom? And what is this thing called the degeneracy or dexterity? Some terms which I think you don't have to worry too much, but just bear in mind. If you see a robot, you should be able to identify is it a dexterous robot or it's a degenerate robot or something is going to go wrong. Okay. To put it in very layman terms, degrees of freedom basically means that number of joints you have for a serial robot. Remember in lecture 1 I talked about parallel robots? You remember what's a parallel robot? You remember? Let's say you have an end effector here. We have one robot here, the other robot also holds on to the same end effector. Right? That is a parallel robot. But we are not talking about that. That one is just for you to be aware of because you may see this robots. But this delay parameter is serial robot. Serial as in you have your base here, and the other end is the hand, the end effector is hanging. It's not connected back to the ground by another robot. So in short, the number of joints you have in a serial robot will be equivalent to the degrees of freedom. Degrees of freedom in the sense that if I have one joint, I have 1 degree of freedom. Right? If I have another joint, I have to be this 1 degree of freedom is another degree of freedom. Total is so on and so forth. I'll test them serially. So the number of joints in a sense gives you your degrees of freedom. Again, your physical space is only how many degrees of freedom in total? What's the dimension number? 6. Right? 3 positions, 3 rotation. Just remember, your physical space is 6 degrees of freedom. And if you dwell more into mechanical design, you only need 6 degrees or 6 jointed robot to fulfill any pose in a physical space. Right? Remember this, okay? But sometimes your tasks don't require all these things. Maybe it's just pick and place. You don't wait for rotation. So that's why you reduce the degrees of freedom or reduce the number of tasks in the robot to create very specific low degrees of freedom. Okay, like things like Stara and Polar and so on. These are meant for very specific applications. You don't need that additional flexibility. So based on this definition I've given you, right? And looking at the arrows as hints, can you fill up this table in 1 minute? Okay, the arrows, these curved arrows and straight arrows represent actuators on the joint. Okay, so what is A? How many degrees of freedom is A?
3,
C,
3,
D,
3,
what about E? 4. Okay. Okay. So remember, in real life, when you see a robot, you go to the why you need to make sure you see what are the joints you have, how many joints you have, each are the basic joints. That will help you to tell you the degrees of freedom the robot has. Okay? Okay? There, in terms of degrees of freedom, there is also some form of mathematical formula to help you to look what this formula does is it looks at the number of links the robot has, the number of joints the robot has, and the number of the type of joints they have, whether it's 1 degree of freedom joint, 2, 3, so on and so forth. This formula can also help you find the degrees of freedom. But for serial robots, it's very straightforward. It's just what we see what we get. But for parallel robots, there is a formula for that. Rulers and criterion equation. But there is something we don't cover, but I just let you know just for if you encounter parallel robots. Okay, the other important aspect of robots that I like to share is this thing called degeneracy and dexterity. Okay. Degeneracy is something like similar to disability of a robot. Now I know that my dimensions can only reach here, but I want to reach the speaker over there. There's no way I can reach. This is what you call one of the form of degeneracy for a robot. It's not a robot's fault, but just that your environment or your task requirements is not suitable for this particular robot. Unless the robot had a long telescopic or prismatic joint allowing to reach. So sometimes robots by itself are not degenerate, but due to the environment or the task requirements make it degenerate. So be careful to select the right robot and select the right robot. The other form is when all your okay, what I mean by the z-axis, assuming that every joint where it rotates, it will assign the z-axis. Right? Now, when all of these joints are collinear or parallel to each other, right? When you go on to look at the Corbin matrix in lecture 6, the Corbin matrix tells you the relationship between the velocity relationship, the joint velocity and your task space velocity, the linear velocity. This matrix also tells you how stable the robot feet will be at this particular pose with this certain. Now, when you have this kind of pose, right? Instantaneously, when I'm at this, can you tell me if the next motion will this joint move to the left or right? Sometimes at this kind of poses, if you don't have proper limits and such, you do not know what will happen to the joint. It's mathematically, it's an issue because mathematically it doesn't know. Although if a theory planning different story. But mathematically, at this particular position, when you find a matrix, the Jacobian matrix, you will find that is called a singularity position. Okay, similar to degeneracy. Okay, so just bear in mind some considerations, although it's clear for you, I don't know which way, but that is more of trajectory planning. But when you look at the mathematics, it cannot handle this kind of problem. Right? It doesn't know what's the next step. Right? So in the sense it becomes a degenerate code. Okay, that's just one example. The other thing is dexterity. Okay? If I have this dexterity means, okay, let's say I do right, physical task is how many degrees of freedom? What's the magic number? 6, right? Instead of having 6 degrees of freedom, I have 7 degrees of freedom. One more extra degrees of freedom. Now what happens is this, you can get the 6 degrees of freedom and the 6 joints, there's something like 6 equations, 6 unknowns. But if you always have 6 equations, but if you have 7 unknowns, your solution is infinite. Okay, it's called an indeterminate system in mathematics. Right? So determinate systems is 6 equations, 6 unknowns. But you have 6 equations, more unknowns, you still need to find something to constrain that one more additional unknowns. But if you don't have, you can still find a solution, but there is a range of solutions. But for a robot, it doesn't know. That is where you need to do this optimization to find that, okay, I found additional criteria. What is the best answer? Right? So dexterity is in that sense. You are giving it a redundant joint so that, okay, I know I can reach this position at this post, but let's say somehow I got some obstacle somewhere here, maybe I can go around the obstacle. Okay? So dexterity is in that sense that you are giving it, you can say dexterity is redundancy. You need, let's say the task space is 6, you need. Okay? So when you see this kind of words in future, don't get shocked. Dexterity just need redundancy. Just that when you are really solving out mathematics, you need to make sure that you find the optimal solution. Because the answers, the solution to your joint angles will be infinite. So many, there are so many options. Okay? Okay. Let's go to these lectures. When you have a robot configuration, you always break down this robot into 2 things. Links and joints. Links will be your standard rigid structures that connects the various joints. Right? And joints basically either can be revolute or static. 2 types. We're not looking at any other type of joints. Okay? So sometimes what you do is this, you know, in this kind of images, well, it's quite fancy, full body kind of images. But what you do later on is to break them down into stick kind of schematic drawings. So you have joints, you have links, you have lines. This is how you break down, and then you will start doing your DH formulation. Right? Now, what this DH parameterization or DH representation does is this. It will help you assign, because what consists in the transformation frame? How many axes do you have in the transformation frame? X, Y, and Z, right? 3, right? End of the day, this method will help you to find X, Y, and Z. You know they are all perpendicular to each other. But how do you position this? Where do you position this? Where should your X be? Where should your Z be? This is the thing, this is the method that helps you to do it systematically. Right? So the first thing that you always do in DH is you always assign axes. Right? You identify your joints. Okay, where are my joints? So you identify your joints, you assign your z-axis. Then after that, based on the way you assign your z-axis, there is a way to define your x-axis. Right? And then after that, the y-axis is just perpendicular to z and x. Right? So it is a systematic way of doing this assignment of your individual axes. Okay? And in this method, there are 4 key parameters. Okay? You have a theta, d, a, and alpha. Theta and alpha, symbolically, you know that these are angles, right? D and A, these are lengths. Basically, what these 4 parameters are doing is this. I have one frame here, another frame here. What I'm doing is, I am moving my x and my z axis by a position and a translation to meet to my new frame. Okay, this is the information that these 4 parameters are going to define. Okay? So you just need to make sure that parameterization, these are the 4 parameters you must know about. Later on, I will tell you how to set up this DH parameterization table and everything systematically. Okay, this will be the 4 parameters. Okay, so as I mentioned, the first thing you need to do is your assignment of your frame. You always start with a Z-axis assignment. Okay, you have only 2 joints, right? I keep telling you prismatic and revolute. Now, a revolute joint where the axis of rotation is, that will be where your Z-axis will lie. Okay. For prismatic joints, it's going to move in and out, right? Then it forms a path, right? That is where your Z-axis will lie. So this is the first step to your frame assignment. You look at your robot, identify the type of joint you have, identify where will be the axis of rotation or the path of motion for prismatic joints, assign the Z-axis. Right? That line you form will be your Z-axis line. Now, whether it's pointing out, pointing in, that depends. Right? There is some flexibility. Right? If you want to make it point out, up to you want to make it point inwards. There's no, they never specify rules for that because it's not feasible to specify any rules. You're going to rotate each other, rotate. But once you define the direction, remember one thing, once you define the direction, then I know what is my positive angle. How? My right hand rule. If my Z is pointing this way, right? My thumb points the direction, my fingers are the verticals tell me the positive direction of my angles. Right? So if my angles is moving inwards, right? Let's say this is fixed, but this thing is moving upwards now. In this manner, this is positive angle. Okay, this is the thing you all need to remember. If this thing, this part is rotating outwards, it's negative angle. Because when you form up your EH representation, this makes a lot of difference, whether it's positive angle or negative angle. Okay. Same thing, once you assign the direction for prismatic, anything that goes in the opposite direction is negative. Straightforward. Okay? But for angles, remember the right angle. Okay. So far clear on the Z-axis assignment? Straightforward, right? You identify your joints, axis of rotation or path of translation, assign a Z-axis there. Okay, whether inward or outward direction up to you. But once you define the arrowhead, then your angles must follow that. The next step is your x-axis. Okay. There is a systematic way to do your x-axis assignment, but it depends on your z-axis assignment first. So you must do your z-axis assignment first. Now, you will have a scenario where you will never have very regular arrangement of your z-axis. It will be skewed. Be 90 degrees, so on and so forth. But there will be 2 cases where you may encounter, and these are some approach where you should follow. Okay, assuming that you start having parallel z-axis. Let's say this is for joint 1, this is for joint 2. Right? Now, the most important rule for your x-axis assignment is this x-axis must be perpendicular to Z1 and Z2. That's the most important rule. Okay? For this scenario, Z1 and Z2, you can assign my x2 anywhere, right? So long as it's perpendicular, it can be at any level, right? Okay, then there is another rule. You look at my x1 and use my x1 direction to make sure that it's fully here or in line with x2. Okay? Remember this, important. Okay. Other scenario which you may encounter, your z-axis intersect. Remember I was telling you my x has to be perpendicular to my current z and my previous z, right? So let's say x2 has to be perpendicular to z1 and z2, right? You remember your cross product? A vector, you do a cross product. Okay, this is different from your right hand rule. is something like this. If you have two vectors, if you do a cross product, if you want to find the direction, maybe Z1 to Z2, you want to find the direction, you also use your right hand. Okay? Don't get confused with the right hand, got a lot of things. Too many things, I don't know why you keep using right hand, but for your angle reference, you also use your right hand. This is different, this is not just, you are seeing from, let's say, vector Z1 to Z2, where is my direction of x2? Because you can point out or point in, right? So you use your right hand rule to indicate that point is going out. So you just use that consistently. So let's say, yeah, you find Z1 and Z2, you want to find x2, so it's Z1 cross Z2, this is the direction of x2. Okay? I know it now is a bit like why is lecturer talking about all these things, but later on you do your question, you realize that all these small little things are very important if you get the right answer. Okay? Okay. I'll just do a quick review first after this, after that we'll go through this more detail. So you know we have these four jointed robot. One revolute joint here, another revolute, maybe this, another revolute here, another revolute joint here. First thing you will do is assign all your Z frames. Right? This will rotate about this and Z will belong to this is along the axis of joint 2, joint 3, joint 4. You all notice something here? Can somebody point to me what is not? Doesn't seem right here. Just look at joint 1, what am I assigning? Z0, Z1. Okay. This is the way the assignment is actually. So if you have joint 1, whatever you assign here will not be Z1, it will be Z2. It's just the way they do it. Why? Because it's your x equals to 1. In fact, when I was working with robots, I used another method, but that is even more advanced. But not meant to be taught now. So this is the basic thing that I can teach you all first. Right? This is something that you all must know. Okay. Anyway, there's a lot of other ways to assign your frames, but it's more the fundamental approaches. Must know this. So take note that if it's joint 1, you will assign Z0, you will not assign Z1. Okay? This will form your base frame in the sense of okay? Same thing, Z1, Z2, Z3. Sometimes the last part, we will also not call it Z3, but maybe we call it ZH. H for hand. Right? Sometimes in your textbook example, they call it H. Right? Just to indicate that, oh, this is the last frame in the hand. Okay. So where will we assign x0 now? There is nothing to refer it to, right? Remember I was telling you your x has to be a common number between the current z and the previous z, right? Z-axis. For the first x0, again, all up to you. You decide how you want to do it. Okay? Yes. So for me, I will decide that okay, I'm going to make this as x0. If you want it to be pointing this way, it's not this way. But make sure that it's perpendicular to your z. Okay? Okay, if I look at so far, okay, let's look at x1. X1 is perpendicular to Z1 and Z0, right? So if you extend this up, Z0, these are all intersecting, right? If we go to this previous example, they are in this format, right? They are somehow intersecting. So if they are intersecting, Z0 cross Z1, you expect it to point out. Okay? Z0 cross Z1. has to be a common normal between, you can't do a cross product, you cannot use a right hand side. Okay? But this is up to you, whether you want to go upwards or inwards. Okay, but remember this thing has to intersect this point. You don't try to offset it. Once you offset these things, you need to look at the origins of each frame. Once you offset all these things, you have to put compensators inside when you're forming a whole table. Okay? Now, Z2 and Z3. They will intersect at this point, right? Z2 cross Z3 will be bonding colors. Okay? Right? What about ZH? Up to you. You can point it out also. Because Z3 and ZH are similar to Z1 and Z2, they are both parallel to each other, but just now they're collinear. So it's up to you whether you want to offset the line or maybe just offset the base. Okay, but remember, these points for XH, they must coincide with this origin. Right? You try to make sure that the origins of the frames coincide with each other, try not to offset.
X1, X2, X3 都看我就
Okay, so this one a brief example now. Okay.
X2 你的 join 2跟 join 3一定要有一个 line intersect 他们。
Do you think I can form my Z and my X again?
现在没有这个吗？还是要 ensure 它 intersect。
What is
这
the
个 frame
property of my this
move to
particular
这个
frame that I have? They are orthogonal, right? Perpendicular to each other, right?
所以可以从这个 frame move 到这个 frame， 放在这个 x axis 上面，再 point 上去。你要 point 上去。
But now it's different. It's not using curly or fingers. Three perpendicular fingers in arm, right? So let's say this is your Z. Your Z is your thumb. X is your index finger. X, your Y will be perpendicular. But the good thing is you don't have to bother with Y. Because we know implicitly that Y is going to be perpendicular to X and Z. In our calculation, we just worry about X, Z and X. Okay? Okay. So again, you may draw some schematics like this. From link N, maybe your joint N is here, link N plus 1. So remember, with this joint N, your Z will be Zn minus 1. Okay, this one I covered earlier, but this is just a general representation. How do we do that now? So your joint N is here, your link N is here. This is joint N plus 1 and then your link N plus 1. Okay? Your link N plus 1 is this plus this. Okay? Don't just think it's just this part, this portion as well. It's a rigid structure by itself. Okay. This is the official definition of the 4 parameters. Okay. You bear with me first. Let's see when I show you graphically, will it make more sense or not going to this one is only stuff. Your transformation from one frame to the other. So what we have covered so far is frame assignments. You assign the Z frame to the X frame. Now is how do we find the transformation matrix. So before we find the actual transformation matrix between one frame to the next frame, we have 4 parameters, remember? I was telling you about theta, d, a, and alpha. So these are the so-called official definition. So if you look at theta, right, the first thing that you do, these are steps we follow in sequence exam out again. You will first rotate about Zn axis by angle theta n plus 1. Right? You what you are doing is this, you have a previous xn axis and a new xn plus 1 axis, right? What you want to do is to make them parallel. Okay? Second thing you will do is you bring these two x-axis together, collinear. That's step 2. Right? Then you have B already. Right? The third is you are bringing this closer to your, you want to coincide this when you move up to your new frame origin. So you're moving by your coinciding your OZN to the ZN plus 1. And then after that, there will be some offset you're going to do at alpha. Okay? This is a very one. You can ask them like, okay? So, what I was elaborating about just now, if you look at it graphically, it will be like this. My first step, okay, this is what I've assigned, right? So in robots, you will have assigned your Zn, your Xn, your Zn plus n plus 1, Xn plus 1, right? So that's clear, right? Assignment. Now we want to bring this point here, this frame here, to this frame here. Okay? What is the first step? This is the first step. You look at this axis, you bring this xn, you shift it here. Now this, when you shift it here, you want to make this parallel with xn. Okay? This step is a transformation matrix by itself. Okay? Later on I'll show you the xn form. Okay? But this is just pure rotation. Second step is I will bring this point up so that it is in line with my xn plus 1. Yes. I am shifting, I'm basically shifting my origin of this field to here by doing it in 4 steps. This is the 4 steps I'm going to do. Okay, so I bring this up here. Third step is I reach here, right? I will do a translation. Translate, I move by a n plus 1 to this point here. Now my origins are coincident, right? But remember, my Zn is still in this direction. I need to orientate it back to Zn. That is my alpha. You need to go through this, you? Yes? Yeah. Let's rewind. The main aim of this is you have 2 frames. You have to bring this frame from this location, this orientation to this location with this origin, this position. 4 steps. Okay. First step is you need to align your xn to my xn. So you're doing a rotation by theta to make them Second step is if I extend this xn plus 1 line all the way here, I'll move somewhere here, right? So I want to bring this back up here. So I will move by dn plus 1 to reach this point. On, I will see n axis. After that, I need to shift this point to my final frame, right? Zn plus 1 to this. Then I will move by an plus 1. But remember, my original frame, yes, my x has been aligned. My z is still not aligned yet. Okay, it's not aligned yet. I still need to do one more last rotation. Okay, so your sequence are 1, 2, 3, 4. Okay, again, the only way to remember this is to practice more questions. Okay, I will pause here for a while, but later on we will show you a method of practice.